And they cannot meet the complex requirements of an automotive fuel cell stack, an automotive proton exchange membrane. And I hope to show you why that is in the next series of slides. First of all, in the case of the gas diffusion media, I mentioned before the gas diffusion media is a graphite fiber paper. In order to optimize the performance of a fuel cell, the surface of that gas diffusion media needs to be as hydrophobic as possible. I mentioned before you need to get the water away from the electrode, and then once you get it to the surface of the gas diffusion media, you need to have it stay on the surface of the gas diffusion media and not permeate back through. And so even though the graphite fiber paper without any coating is fairly hydrophobic, it's about a 100-degree contact angle, you actually need to go even higher than that in order to completely keep that water away from your electrode surface. And the way that was done in the past is by coating the paper using highly dispersed particles of polytetrafluoroethylene, particle sizes of about 30 nanometers. And so the process that was typically used is that the paper was dipped into the suspension of PTFE nanoparticles. These particles are prepared by emulsion polymerization. Various surfactants are used both during the polymerization process and also to maintain suspension stability. And then it was dried very rapidly in an oven, and the reason rapid drying was used is they wanted those PTFE particles to segregate on the surface of the diffusion media. And you can see that in these EDS maps that I show here. The high intensity areas represent, or the white areas that you see here, represent fluorine counts. Okay? Fluorine coming from the polytetrafluoroethylene. Graphite fiber paper has no fluorine in it, and so you can associate the fluorine directly with the PTFE particles in the gas diffusion media. What you're looking at here is a cross-section of that diffusion media, which corresponds to the cross-section that I showed you in the schematic previously. And so you can see after this particular process, the fluorine segregates to the surface, and you can also see that on this map. You have fluorine counts on the y-axis. You have an arbitrary z dimension, and as soon as you encounter the diffusion media surface, you can see high intensity fluorine intensity, and then when you get through the bulk of the gas diffusion media, that intensity drops off. Doesn't completely go to zero, so there's still particles in the bulk of the diffusion media, but in general, they're segregating to the surface. And this is a high resolution SEM image, a field emission SEM image, where you can actually see here the individual PTFE particles sticking on the surface of the gas diffusion media fiber. The gas diffusion media fiber is about 8 microns in diameter. So you can see here the scale bar at 1 micron. So you can see this, for this process, these particles do not completely coat the fiber surface. Actually, they're fairly dispersed. And from a wetting standpoint, you can see what the introduction of PTFE fibers does to the macroscopic contact angle. This is a dynamic contact angle trace where a sample is being immersed into the wetting liquid, and the force that that liquid exerts on the sample is monitored. And by subtracting away the buoyancy force, leaving only the effect of surface tension, you can actually calculate what the contact angle is. And so this is the mass, the effective mass, that is experienced as the sample is advancing into the liquid. And this is the effective mass that's experienced as the sample is being withdrawn away from that liquid. And so you can see that we can achieve fairly high macroscopic contact angles, about 167-degree contact angle. However, we need to be careful in our interpretation of this result. This is a macroscopic contact angle, okay? And it is not necessarily related to surface coverage of these particles on the diffusion media. You saw in the previous slide that we actually have a highly dispersed system of these particles. And so this represents an average wetting across the surface of a diffusion media. And so macroscopic wetting can be insensitive to wide variation in surface chemical composition, especially when you see this hysteresis being present. Typically, the advancing contact angle is representative of the hydrophobic regions of the surface, whereas the receding contact angle is more representative of the more hydrophilic regions of that sample. And so 167 degrees is what you're seeing as the PTFE particles themselves, whereas this receding contact angle is more representative of the fiber surface, the carbon fiber surface. What was observed in the past was that despite careful control on the loading, the absolute amount of PTFE that was taken up by these papers, there was still poor performance in the fuel cell stack where these gas diffusion media were employed. And it wasn't, all of the gas diffusion media weren't failing. This is an example of a characteristic performance of a 30-cell stack. And let me describe what exactly is being done in this experiment. What we're doing is we are dropping off the flow on the cathode side of the cell as a function of time. And so these steps represent a dropping off in the flow. Okay? And we're monitoring how long it takes for the potential across that cell to drop off. And we're monitoring the performance of each cell in this 30-cell stack. And you can see that after a certain period of time and at a certain stoichiometry, a certain flow, we start to have cells dropping off. Okay? And eventually, at long enough times, all of these cells will drop off. Okay? This behavior is unacceptable, and it's an indication of flooding. It's an indication that the diffusion media has been overwhelmed by the presence of water on its surface. Essentially, all the pores in the diffusion media are being blocked. We're not able to get reactant gases to the electrode surface, and it's unacceptable. And so the question, our first question was, in this particular project, what differentiated these diffusion media, or the treatment of these diffusion media, from the remaining diffusion media? And so we wanted to focus on whether the PTFE nanoparticle distribution on the surface of the GDM and the associated microscopic wetting behavior, in other words, the XY distribution of these nanoparticles, is more relevant to GDM performance than the macroscopic wetting and cross-sectional PTFE distribution. As I indicated before, the macroscopic wetting does not really tell us much about the microscopic distribution of phases on the surface, chemical composition on the surface. And so the approach was to employ various surface chemical analysis techniques in conjunction with environmental scanning electron microscopy to answer this question. And here are some of the results. So initially, we just did a screening study. We took a large assortment of papers, knowing which papers failed and which papers did not fail. And we did EDS on these papers. We knew that all of these papers had similar loadings. So in terms of a weight percent that you could characterize directly using TGA. So in other words, you could burn off your materials using TGA and know precisely how much PTFE had been loaded in a macroscopic sense, an average sense, on that diffusion media. And so all these papers had similar loadings, okay? Variation in performance. And we analyzed the surface of these materials with EDS to look at the, well, in this case, we plotted the results in terms of the carbon to fluorine ratio. Carbon coming primarily from the carbon paper, and fluorine being unique to the PTFE particles. And so this was very interesting initially. Despite similar loadings, we're getting significant fluctuation in this carbon to fluorine ratio. Okay. In the case of pure PTFE, this ratio would be, you would have 2 fluorines to every carbon, so you would be at 0.5. So very low levels of this ratio indicate high fluorine content on the surface. And conversely, very high carbon to fluorine ratio indicates very low fluorine on the surface. And very puzzling despite the controls. The other thing I should mention is we also did cross-sectional analysis for the fluorine intensity as a function of the z direction. And we saw there again that we were getting the fluorine segregating on the surface. So these results initially were very puzzling. Why we're getting fluorine segregating on the surface? We have the same absolute amount of fluorine in these materials, and then we're getting this significant variation in EDS carbon to fluorine ratio. Also, unfortunately, I cannot tell you where the where the good papers were and where the bad papers were, but we did get some clearly delineated regions of performance. In other words, there were papers of a given carbon to fluorine ratio that had very good performance in a stack, and others within a region of carbon to fluorine ratio that had very poor performance in a stack. And so the next step we took was to actually do a mapping, an EDS mapping of the surface of this gas diffusion media. And these are a couple of those EDS maps. The red color indicates the graphite fiber paper. These are the graphite fibers, and again, the diameter of each of these fibers is about 8 microns. And the cyan color indicates the fluorine, the PTFE particles. And what we saw is we saw significant differences in how these PTFE particles distributed themselves on the surface of the gas diffusion media. In some cases, we saw that these PTFE particles tended to aggregate at the intersections of the carbon fibers. Other situations, we saw that the PTFE was much more uniformly distributed. We started to see quite a bit of the PTFE actually on the surface of the gas diffusion media fibers. And this difference in mapping was directly related to the carbon to fluorine ratio that we were observing. So whenever we had a very low carbon ratio, apparently a very high fluorine content, we got segregation or aggregation of these PTFE nanoparticles. And conversely, when we had a very high carbon to fluorine ratio, we've got a much more uniform distribution of these PTFE nanoparticles. And this was true despite the fact that, as I mentioned before, the z-directional distribution of these nanoparticles was identical. Very little in the bulk of the diffusion media, segregation at the surface, whether we were seeing high carbon to fluorine ratio, higher carbon to fluorine ratio, or low carbon to fluorine ratio. So to understand this seemingly contradictory behavior, we undertook some Monte Carlo simulations for the path that an electron beam will take in carbon. And in this particular simulation, you see that the penetration depth of the electron beam, now remember in EDS what we're doing is we're actually looking at the X-rays that are being emitted from the sample when it's being impacted by the electron. When electrons are being scattered in the sample, it's generating X-rays. The X-rays can generate other electrons in the sample, but they can also be measured. And so our penetration or our analysis depth is really not controlled by the X-rays, because the X-rays can penetrate very deeply into a sample, but it's in fact controlled by the electron scattering within the sample. And so from these Monte Carlo simulations, we saw that we were only penetrating about 5 to 6 microns into the fiber surface. Remember, these fibers are about 8 microns in diameter. So during our analysis using EDS, we were not completely penetrating through the surface of the GDM, completely through the fiber. And so this helped explain this appearance, or this relationship between carbon to fluorine ratio and surface distribution of the PTFE particles. When we had segregation of the PTFE particles at the intersections of the gas diffusion media, a significant fraction of those PTFE particles were invisible to our EDS analysis. However, when we had a more uniform distribution of these PTFE particles across the surface of the diffusion media, more of those PTFE particles were present in our analysis. They were not being hidden by the fibers themselves. And so this provided an explanation to us of why we were getting this correlation between this very simple analysis of carbon to fluorine ratio and the maps that we were generating. So a very nice way to avoid, generating maps can be very time consuming. Each map can take half an hour, 40 minutes. whereas an analysis simply of the average carbon to fluorine ratio can be done in a couple of minutes. So significant time saving for us when we establish that correlation. And we also did XPS, X-ray photoelectron spectroscopy analysis, which is much more surface sensitive than EDS. With EDS, you're talking about 5-6 microns penetration depth or analysis depth. With XPS, with EDS, you're looking at the X-ray photons. With XPS, you're looking at the kinetic energy of the electrons, and electrons can be very easily scattered by nuclei. And so really here you're only probing maybe the topmost 2 atomic layers of your surface. So very, very surface sensitive technique. But it showed us that when we had a high carbon to fluorine ratio, this corresponded, let's see, yeah. So when we had there we go. So the high, if you go through, this is the carbon fluorine ratio from EDS, this is the carbon fluorine ratio with XPS, and you see a correlation between the two techniques. Basically, high carbon to fluorine ratio corresponding with high carbon to fluorine ratio on XPS. Okay. And also that corresponded with Auger as well. So here we were trying to use an entirely different technique in order to confirm our elemental result that we were getting with EDS. So then the next step was, well, how does surface distribution of PTFE correspond to microscopic wetting behavior? And so to answer that question, we used ESEM. And here you see the ESEM result in this experiment. What we do is we increase the vapor pressure of water in the analysis chamber in order to get above the saturation vapor pressure of water at 5 degrees centigrade. And we begin to see condensation of water on the surface of the gas diffusion media. You begin to see droplets forming on the surface of the gas diffusion media. And what we saw was that when we had a very non-uniform distribution of PTFE, again, very low carbon to fluorine ratio, we were getting a significant number of droplets condensing on the surface of the gas diffusion media. And this particular image was taken right before the surface was completely flooded. That is, eventually, if you waited a few more seconds, these droplets would connect with one another and form a continuous film on the surface of the gas diffusion media, which completely blocked all the pores in the gas diffusion media. When we had a more uniform distribution of these PTFE nanoparticles, we saw a fewer number of droplets condensing on the surface, and so they were able to grow to a much greater size before they contacted one another and coalesced into a continuous film on the surface. And so effectively, you had much more time before the pores were blocked when you had a more uniform distribution of PTFE than you did when you had a non-uniform distribution of PTFE. So the final film that formed on this surface was about 80 microns in thickness, whereas in this particular surface you exceeded 100 microns and you were approaching 150 microns before the film, the droplets coalesced into a continuous film on the surface. And so one can create a very simple model looking at the time it takes for these droplets to coalesce into continuous film and compare that time to the reaction that's taking place in our fuel cell. So if the production of water continues, you're going to get continual growth of these droplets. And eventually, regardless of what the treatment of your diffusion media is, you're going to get film formation and your performance is going to drop. All your cells are going to drop out. But if you can form a thicker film before your pores are completely dropped, you actually have more time before your cell drops out. And it's very important when you're talking about a cyclic operation of a fuel cell. In the experiment that I showed you before, where we were continuously dropping off our cathode stoic as a function of time to see which cells were most susceptible to flooding, that wasn't representative of the operation, the actual operation of an automotive fuel cell stack. In the operation of a fuel cell stack, your power is actually cycling. Okay? Sometimes you need a lot of power in order to accelerate, and other times you need to back off on the power when you're coming to a stop. And so your water production is cycling. High power requirement, high current density, much more water being produced, and conversely for low current density, low power requirement. And so you have significant fluctuations in water being produced in your fuel cell. And so if you have a diffusion media which can remain porous for longer periods of time, that results in better performance ultimately in your automotive fuel cell stack. And so, okay. So one thing you can do, one approach, is once you've been able to identify what PTFE distribution is optimal, what carbon to fluorine ratio is optimal, now you can go back and actually sort your diffusion media before you put them in a stack for that optimum carbon to fluorine ratio. Okay? Not a very efficient way of doing things. This was the work that I did at General Motors, and I assured my management that we would only do this for a very short period of time. Because you can imagine how time-consuming that is. You have to go through, pre-analyze all your gas diffusion media using EDS, sort through them so that you know which GDM you predict will be good, which GDM you'll predict will be bad, and then designate those to go into a fuel cell stack. And although it's not a very efficient approach, nothing you would want to do in the long term, it was a very successful approach in that before we started our sorting procedure, this is region 1, 64% of the stacks that we were building required repair for this poor performance. And what was the repair? The repair was the cell was taken apart and the diffusion media was replaced. So randomly we were getting good papers in our fuel cell stack, but a significant repair rate, very, very costly. In region 2 and 3, that was the point where we instituted our sorting procedure. A very painstaking procedure. But you see that the repair rate dropped down to 0. We had one excursion here that we were able to relate back to a plate issue, nothing to do with gas diffusion media. But this was a very successful approach, but nothing you would want to really live with in the long term. But at least it confirmed to us that improving the controlling, I should say, the distribution of the PTFE nanoparticles was a way of significantly improving your fuel cell performance. And that was the conclusion that we reached in this initial study. PTFE distribution can vary significantly on a GDM surface, both macroscopic, absolute uptake, but more importantly, microscopic, three-dimensional distribution variations are important. EDS is a reasonable way to characterize the microscopic distribution. And fuel cell performance may be optimized by controlling the PTFE distribution. But that wasn't good enough, because now that we knew what the impact of PTFE distribution was on performance, we wanted to come up with a way of controlling that PTFE distribution. And our initial thought was that perhaps we could do it through chemical interaction between the graphite fiber surface and these PTFE particles, because during the emulsion polymerization process, the surfactant that's used as the polymerization surfactant is being incorporated into the particle structure. And so we were thinking initially that perhaps we could use interaction between that surfactant and hydrolysis of the graphite fiber surface in order to control specifically how those PTFE nanoparticles distributed themselves. Unfortunately, that was not a successful approach at all. It turns out what we discovered that drying conditions were more important than anything we could do chemically to these materials. Okay? And I have an experiment which shows this very dramatically. This is an experiment where we did a freeze drying study. And what we did is we dipped the gas diffusion media into the suspension of the PTFE nanoparticles, and we immediately froze the sample liquid nitrogen. And then we sublimated the water away and left the PTFE particles behind. And what ended up happening is we saw these PTFE particles being left behind in a very random fashion. They really weren't related to the fiber structure at all. And that was a very strong indication to us that really there was no chemical interaction taking place between the graphite fiber surface and these PTFE particles. These PTFE particles were basically going to stay with the water. They were going to follow wherever the water went. And so we discovered that if there was a way that we could control the distribution of water, we could in fact affect the distribution of these PTFE nanoparticles on the surface. And these are just some experiments that we looked at doing that. What you're looking at here is the very slow evaporation of water from the surface of a gas diffusion media. And what we found is that in this situation, we could get an excellent distribution of PTFE nanoparticles on a surface versus a more rapid drying. What we saw with a more rapid drying was that the water, rather than being distributed across the entire surface of the GDM, would immediately associate at the intersections, or clump at the intersections of this GDM, and those were the samples where we got a very non-uniform distribution of the PTFE. And so, well, now that well, let me take a step back a little bit. This particular image was taken with stagnant air conditions, overnight drying. It's really not a way you want to run a process. A process that takes 24 hours to treat a surface. So we came up with other approaches of controlling the drying of water. And unfortunately, I can't talk about those approaches. The patent is close to being issued. I think it may have already been issued. But suffice it to say, in order to control the distribution of PTFE particles on graphite fiber paper, you need to control the drying of water very carefully. And so there are various approaches that can be used to control the drying of water. And this is the result of one of those, the more successful approaches. So this yellow line indicates the performance of graphite fiber paper that were prepared controlling the drying of water. Purple and blue are some papers that we received from some vendors at the time that had a more non-uniform distribution of these PTFE particles. And we were able to extend the lifetime under these test conditions significantly. And so, okay, actually this patent was just published 2006. I thought it was still a pre-grant, but I guess I must have made this modification in this presentation. So, so you can get the details there. I suppose I can release it at this point. The key for us was microwave drying. Okay. Using microwaves, you can get very fine control, and using waveguides, you can get very fine control of exactly where these PTFE particles are distributed. And that's actually the focus of our future work in this area. We would like to use waveguides, microwave heating, in order to control specific regions in this gas diffusion media, which are hydrophilic and which are hydrophobic. Okay. And so that's the major thrust of our future efforts. So the next area where nanotechnology is important is in terms of these bipolar plates that are used in a fuel cell. There again, surface wetting is very important, but in this particular situation, rather than having a very hydrophobic surface, you need a very hydrophilic surface. And that's because you need to be able to move the water through these channels and expel it out of your fuel cell into a series of manifolds. If you have a hydrophobic surface, that surface is more susceptible to capillary-driven instability. And what that ends up giving you is these slugs of liquid water in your channel, which are very difficult to remove using the stoichiometries, the flows that are presently used in fuel cells. We found that if you have a more hydrophilic surface, it makes it much easier to move that liquid through the channels in your bipolar plate. And so the way we did these initial experiments was with plasma. processing. We basically introduce hydrophilic functional groups onto graphite epoxy composite plates. Conductive materials, as you may know, are very hydrophilic materials, whether you're using a metal for a bipolar plate or whether you're using a graphite composite the way the industry has done in the past. It's a very hydrophobic material. And so we carried out our experiments using dry chemical processing, and we were able to prove out this mechanism, but the problem is one of scale. Okay? Dry processing equipment is very expensive to purchase, very difficult to maintain. Essentially, you need a PhD dedicated to that equipment to be able to keep it running smoothly. Very difficult to put in a manufacturing setting. So we started to explore other alternatives, such as spray-on hydrophilic materials. We found very poor durability in these spray-on coatings. Surfactant residues, typically these spray-on coatings have surfactant residues. We found them leaching into our system. We found very poor adhesion between these coatings and the bipolar plate surfaces. And so what I did is I reached back into my background in microelectronics, where I had actually used electrostatic interaction between adsorbent species in order to create very durable coatings in microelectronics applications. And in this particular application, a cationic polymer is adsorbed onto an epoxy printed circuit board surface. It imparts a cationic charge to that surface, and then you can actually attract negatively charged colloidal catalyst particles onto that surface. In this particular application, these were palladium catalyst particles. And these are basically, we put out a series of patents that, I think the first one came out in '98, the most recent one came out in 2002. But this particular patent gives a good summary of the approach. And we were able to catalyze the surface, and that's it. This is actually the approach that's being used today to electrolysely deposit copper onto an insulating surface. You can deposit copper either electrolytically or electrolysely using this approach. And so with that background, we went back and we tried to see whether we could use a similar approach to create a hydrophilic coating on a bipolar plate surface. So this is the details of that approach, or a schematic of that approach. You're looking at a cross-section of the bipolar plate surface. You're depositing a cationic polymer onto that surface, and you're depositing an anionic nanoparticle. In this case, we wanted a hydrophilic nanoparticle. And you repeat that process in order to build sequential layers. A number of people have been doing this in the laboratory for many years. But really, the microelectronics application I referred you to previously was the most commercially successful application of this multi-layer self-assembly approach. But we wanted to see whether we could be equally successful in fuel cells. Actually, the approach was first proposed back in 1964. People have been doing a lot of things with it since then, but really commercially it hasn't been proven out except in that microelectronics application and in this fuel cell application that I'm going to be describing. So the key advantages of this approach is the process occurs in the liquid phase. It can uniformly coat large and complex shapes. There are no shadowing effects that typically occur with dry chemical processing approaches. But unlike standard wet chemical coating approaches, you can get nanoscale control over your structure, the coating structure. And that's very important here. I mentioned before that we need coatings in this particular application that are not only hydrophilic, but also conductive. Okay? It's very easy to apply a hydrophilic coating on a surface, but trying to make that conductive is a very difficult thing to do. And so we felt that this self-assembly approach gave us the best option of doing that, aside from dry chemical processing. And the process can be inexpensively implemented. There's a lot of research involved in formulating the suspensions that are used in self-assembly, but once these suspensions have been formulated, the manufacturing process itself is very simple to carry out. Essentially, you can use dip tanks that are common to the microelectronics industry. And we found that because of strong electrostatic interactions between the layers, in other words, you're relying on true adhesive bonding between each layer and the substrate underneath. You're not relying on cohesive interactions of the coatings laying down on the surface for durability. When you're relying on cohesive interactions, any cracks that start to form in your coating, and your coating will start to come off in chunks. And that's what was happening to us with our spray-on coatings. That never happens in this situation. With these electrostatic interactions, a very strong bond, strong adhesion to the substrate. No cracking. And so in the multi-layer formation process, again, very simple. Now, a lot of sweat and tears go into formulating what is in each of these baths, but once you do that, then it becomes a dip process. You take your substrate, dip it into your cationic polymer solution, rinse that surface very carefully, because again, remember, we're interested in adhesive interactions between the substrate layers. And so you want to remove any residue that is not tightly adhered to the surface you want to remove. Then you dip it into the an aqueous hydrophilic suspension. In some of our studies, we used a silica dispersion. And so you do need to use surfactants in order to maintain stability in these dispersions, but the nice thing about this process is, again, you go in and rinse away any low molecular weight residues, any surfactants they're using to stabilize your dispersion. You just rinse it completely away, and you deposit. You can repeat this deposition process as many times as you want to create very, very well-controlled nanolayers on the surface. We've gone down to as small as 5 nanometer particles in this process, and have been shown that we can get fairly linear deposition of these nanoparticles out to, we really never saw a saturation point. So you never really get, using this approach, you never achieve charge neutralization. Okay? If you ever neutralize your cationic and anionic charges, your deposition process would stop, your uptake would saturate. That never happens, at least in the systems that we've investigated, whether it's palladium nanoparticles on this cationic polymer, or silica nanoparticles, or other nanoparticles that we've investigated, gold. We really have not seen charge neutralization, continuous uptake in a very well-controlled fashion. So a resolution down to 5 nanometers in the Z direction. And so this is some of our results. Here you're looking at the surface of a bipolar plate. You're looking at the serpentine channels. This is the color of a plate surface that has not been treated with silica. In this case, this is the result with silica particles. And you can see that the color of the surface changes with the thickness of the silica that you're depositing, the silica layers that you're depositing. And it is very interesting and very, very encouraging that the color dependence on thickness of these silica nanoparticles is identical to what you would see with thermally grown silica. Okay? That gives you an indication of how densely packed these structures are, very coherent. If you use spray-on coatings of these silica nanoparticles, you would never see any change in color. There are so many surfactant residues present inside the coating. You really would never get a densely packed structure of these silica nanoparticles. And yet, so imagine here, instead of using a dry processing set of equipment, we're using beakers on a laboratory benchtop, and yet we can create these very dense coatings on surfaces. And this describes the uptake both in terms of thickness and in terms of elemental composition, here atomic percent silicon, as a function of the immersion cycle, number of cycles. And again, we were able to carry this out to many, many layers. In this particular experimental result, you're looking at a substrate which is a graphite epoxy composite. We've shown that we could do the same thing on metal surfaces. This is a gold substrate, and again, you can see the variation in color with thickness of the multi-layers that are deposited. And the behavior here is not quite as linear. Eventually it does become linear, but initially we are getting some non-linearities here. But it never turns over. It never saturates completely. It continues to increase. So very, very encouraging results. Complication is that these silica multi-layers, although very hydrophilic, super hydrophilic, contact angles less than 10 degrees, very attractive, just what we needed. Fortunately, silica is an insulator. And so the silica coating will gradually wear away. It will gradually dissolve in the acidic fuel cell environment. But the way you can get around that is to create a thick enough coating. Unfortunately, when you create a thick enough coating to be durable in a fuel cell environment, your potential drop is significant. On a gold substrate, to get a durable coating, you have a potential drop of 0.2 volts. On stainless, 0.6 volts. That is completely unacceptable when you're talking about a potential at 1 amp per centimeter squared with all of the efficiency losses. Your potential is really no better than 0.7 volts. So really the fuel cell industry is scrambling for every single millivolt that you can get out of a stack, and you cannot live with 200 millivolts. And so the next phase of our project then, well, first of all, the initial phase of our project conclusion is multi-layer self-assembly may be employed to create durable coatings for the fuel cell industry. However, new self-assembly approaches must be developed to create multifunctional coatings, coatings that are both hydrophilic and conductive. And so this was our dream when we first started out, basically have a structure of this type. You just need to use the cationic polymer as a binder, as it were, to provide electrostatic interaction. But now, do something that really has never been done before. Create a mixed, self-assembled, multi-layer system. So you're mixing in a single layer, you're mixing both a hydrophilic material and a hydrophobic conductive material to create a well-defined nanoparticle array in the XY direction. So we know we can get 5 nanometer resolution in the Z direction, but can this actually be achieved? Nobody had ever done that before using this self-assembly multi-layer approach. Preliminary results are very encouraging. Now, I don't want you to get the impression this was our first try. Actually, our first try at this gave a worse result than we were getting with just silica. But eventually, we were able to arrive at a formulation. We were able to create well-defined arrays of nanoparticles. The dark areas that you see here are only conductive graphite nanoparticles. And the light areas that you see here is composed only of hydrophilic silicon particles. Very important. And this was done with a self-assembly process, so a dip tank beaker process. So we're very, very gratified at this approach. Fundamentally, again, I can't talk about the details, but fundamentally it only employs interactions between nanoparticles and polymers, both repulsive and attractive interactions. But being very careful with those interactions and being very creative in the sequence of deposition, you can create these two-dimensional arrays. And the result was also very gratifying. Now we're down to 40 millivolts. This now gets us into the target of the potential drop that we would like to see across that coating. 20 millivolts really is our target. 40 millivolts is much better than what we've seen before with just the silica. And I hate to say it, but our initial results trying to create a conductive coating nearly doubled the potential drop or the contact resistance. So there is quite a bit of understanding that needs to take place in order to create these two-dimensional arrays. Okay, so now I have maybe 5 minutes left. I'll get into the membrane electrode assembly. Currently, the electrodes are prepared using these colloidal catalyst slurries. They're formulated using the perfluorosulfonate ionomer that's used in membranes, number of solvents, and highly dispersed carbon-supported platinum catalyst nanoparticles. The application of the slurry can occur directly onto the membrane or onto a decal, which is then hot pressed onto the membrane using very simple Meyer rod techniques. So very rudimentary approach. Surprisingly though, this very crude approach gives excellent beginning of life performance. So nature is very forgiving in this particular situation. Very high performance, very crude approach. However, nature is not forgiving when it comes to durability. These electrodes degrade very quickly. You may have heard as recently as even a year ago that currently the durability of fuel cells is limited by the proton conducting membrane. It's no longer the case. During my last year at General Motors, we were able to overcome that problem with membrane durability, and now we have membranes that last many thousands of hours. The durability target for fuel cell applications is 5,000 hours. Membranes that we developed for General Motors now last 8,000 hours and beyond. So membrane durability is no longer an issue. Now these are perfluorosulfonate membranes and they are expensive, but really no hydrocarbon alternatives have been found. Right now what is limiting the durability of fuel cells is the electrodes. This slurry that is being produced using these very crude techniques. High beginning of life performance, great, very poor durability. What are the degradation mechanisms? Various observations have been made. People have observed a migration or loss of platinum catalyst, sintering of platinum catalyst, corrosion and loss of the carbon support itself, disruption of the PFSI network. The electrodes apparently fall apart in some situations under some operating conditions. But the main problem is that no one yet understands the root mechanism responsible for electrode degradation. And the main reason for that, well, two reasons. One of these is it's very difficult to observe fuel cell operation in situ, electrode degradation under in situ fuel cell operation. But the other important reason that the mechanism has not yet been established is because these crude approaches for making the electrodes produce very ill-defined nanostructures. It's very difficult to look at an image of an electrode when it is brand new and an image of an electrode after it has been degraded and see precisely what the mechanism of degradation was. And I can show you a high-resolution SEM image of the state of the art in electrode production now. What you see is these are the highly dispersed carbon particles. Each of them contain the platinum. There are aggregates. There is the perfluorosulfonate ionomer, which serves as a binder between these particles. The fluorosulfonate ionomer is very important because that's what supplies the protons to the catalyst surface. And then you have these open areas where you have the reactant gas being transported. And so if you look at a cartoon of the electrode, what you see is that you need this PFSI membrane to provide proton transport. You need these open areas which provide oxygen and hydrogen, the fuel, and also which allow the liquid water to permeate out. And here are your carbon, or your platinum nanoparticles on your carbon support. The primary particle size of your carbon support, well, that can get down around 50 nanometers. But really, ultimately, when they're used in this paste, the carbon support is aggregated to the point where you have aggregate sizes of about 2 microns, 5 microns. And so ultimately, when you put these aggregates down onto your surface, when you coat them onto the surface, you get this random assembly of materials. It's very hard to ascertain from that precisely how your PFSI network is being disrupted, precisely what causes carbon corrosion. And so what we have proposed and what we're working on right now is to fabricate PM fuel cells using this multi-layer self-assembly approach that we have previously shown to be so successful in creating coatings. But as a first step in creating multi-layers, characterizing the nanoparticles that are employed is very important. If you're going to use electrostatic interactions, you need to know exactly what the electrostatic charge is in each material, how you can modify that charge. In some cases, you can modify the surface with pH, and I don't have time to get into it, but those are the kind of studies we've been performing on these carbon-supported platinum catalyst particles. In this case, we're looking at graphite nanoparticles. Carbon black has been used extensively in the industry, but we feel that using graphite will help with corrosion of the carbon support. And so this is just an example of the type of experiments we have been doing, looking at suspension stability of these graphite nanoparticles as a function of pH. And so you can see here that
here. So it's our great pleasure today to welcome our speaker. We have Dr. Anastasios Angelopoulos, who has a very diversified background, both in academia and industry. Tasso, don't try to pronounce his name. it means something very nice. It means he's a man who is like an angel. So he must be a good man. And he has a very diversified background, as I said, both in industry and academia. He got his BS and master from University of Tufts in Boston in 84 and 88 respectively. Then he joined industry. He worked for IBM. He got several patents in microelectronics and some very fancy things he was doing there. And then he decided to go back and do his PhD. So he graduated from Princeton in '96 with his PhD. And then joined another big company, General Motors, and he became one of the experts in fuel cells. He has over 25 papers. He has 9 or 10 USA patents. And we hired him last summer in order to build our research in fuel cells, membranes, and many other things. We have hopes he will be doing a lot of great things soon. He cannot talk very much about details, I think, today, because he got already some grants from industry. And you know industrial people, they don't tell anything. And he's an industrial man, so he knows the game. So today he's going to talk to us about some work he started in Cincinnati for fuel cells. Thank you.